Hello everybody, welcome back to another Strengths Materials video, and this one's going to be super simple. It's on superposition, which is related to a concept we've already talked about called deflection and slope by integration. And we're going to use some of the concepts from that video to figure out where these formulas are coming from. And if you want to watch it, feel free to click the link up top. But we're going to use those concepts to solve this simple problem here. And it goes as follows. The W10 by 15 cantilever beam is made of A36 steel and subject to the loading as shown. We have the 4 kip and the 6 kip at the midspan and end respectively, and we find the displacement at B and slope at B. That's what it's asking in the problem, and B is right at the end over here. Now, why do I bring up this previous video, and why am I writing down this formula over here? Well, this formula was solved in the previous video, and all it pretty much means is that if we integrate the load function 4 times with respect to x, and then bring over this EI, we can actually solve for the deflection based on that original load function, which is pretty cool. But the main takeaway from this derived equation is that the load function Wx needs to be linearly related to the deflection y. So why is that important in our case? It's important because if we had multiple loads to solve for on a beam span, then we can derive individual equations for slope and deflection at these points and cumulatively add them together in order to solve for the total effect from both of the loading at a individual point. Okay, so that's where superposition comes in. All that means is that we're going to be adding cases together in order to solve for max slope or max deflection at this endpoint, for example. But in other cases, you can solve for equations at any point using the elastic curve equation, which is something we talked about in previous videos. But this one's super simple because we're asked for the slope and deflection at the end span, which is always the max point of deflection and slope for a cantilever. So we have lots of predetermined formulas to solve for this in these tables. And you can search these tables online. If you just simply search slope and deflection of beam tables, you'll find something that looks super similar to this. And you can see we have both of our loading configurations here. We have the midspan load and we have the end span load. And both of these equations, or both of these scenarios, have generated equations for the max slope and max deflection at the end. And if we add these together, you will end up with your final answer for this problem. So let's go ahead and start solving it by looking at the first case, which is where we have the point load at the midspan. So if we wanted to find the max deflection, which would be at point B, we are simply going to be taking this formula right here. So what do we have? We have -5. We have the point load, which is 4 kip. We then follow that up with the length, L. Now don't get tripped up here. It still wants us to use the full length of the member. So we're going to have 6 plus 6, which is going to be 12 feet. And that is going to be cubed. And then all of that is over 48 EI. Solving for this, you're going to be left with 720 kip foot cubed. That's all over EI. And this is a negative, but if we look at our beam, the deflection is going to be below the x-axis, meaning that we're actually deflecting downwards. And then similarly, we have the max slope, which is happening at point B as well. So we can go ahead and use this equation over here too. So we have a negative, what are we looking at here? We have a -4 kip, obviously, right? And then we have the length squared. So we have 12 foot, and then that's going to be squared. And all of that is over 8 EI. And then simply solving for that, we have 72 kip foot squared this time over EI. And our deflection, or our slope, sorry, is going to look something like this, where we are sloping below the x-axis. Okay. And we can do a very, very similar thing for the second point, where we are simply plugging and chugging into these equations once again. So I'm going to go ahead and do that for the slope and deflection for the second case, where we have a 6 kip load now. Alrighty, so now we have the max slope and max deflection solved for both of these loading cases at point B. Now all we need to do is simply solve by adding these together. So let's do the deflection at B first, which will simply equal to the max deflection for case 1 plus the max deflection for case 2. And when we add those together, we're going to have 720 plus 3,456, which is going to leave us with a number 4176, and that is kip foot cubed over EI. But let's go ahead and start plugging in our EI values to determine the exact deflection for this specific beam. So our E is 29 times 10 to the 3, and that is kip over inch squared for KSI. Sorry, that should be a 2. And then we have the I, which is 68.9 inch to the 4. And then on top, we have to convert this foot cubed into inch cubed, and the conversion is going to look something like this. We have 1,728 inches cubed per foot cubed. Alrighty? Now solving for that, you are simply left with 3.61 inches, and that is downwards once again. Similarly, you did the exact same thing for the max slope, or the max slope at B, which will be equal to the summation of the max slope from case 1 and the max slope from case 2. And you are left with a final answer of 0.0363 radians. Once again, with the convention of rotation right here as shown, rotating below the x-axis. And those are your two final answers for this super simple problem. And I hope it helped.